Okay, let's look at ohmic and non-ohmic conductors. An ohmic conductor should have a resistance that's constant, and a non-ohmic one will have one that changes. So one of the ways to test that experimentally is to connect up a particular thing you're trying to test, put a voltmeter in the circuit and an ammeter. Similar to what I've done here. So you can add a voltmeter in there and the ammeter's on the other side there. And if you measure the voltage versus the current, for different voltages you get different currents there. If you end up with a line of best fit through all the crosses that's actually straight, like this here, so you've got a constant slope, it means the resistance is actually constant and the conductor should be ohmic. And one of the ways of looking at that is that what you've got here is a few things you can conclude. First of all, because it's a line of best fit that's straight and going through the origin, you can conclude that voltage is proportional to the intensity of the current. But if you then look at the thing in more depth as a mathematical formula, it's a y equals mx plus c graph. On the y-axis you've got voltage. The slope here represents m, so let's say you had a slope here of 5. You would get 5 replacing there, and the x quantity is I. And the c is normally the y-intercept. In this case there isn't one, so you can come up with the formula there that v is equal to 5I. Now if you compare that to Ohm's law that v is equal to IR, you could rearrange the Ohm's law one so it looks the same as your practical result. And you should be able to then see that they line up. The voltages are lining up here, so your practical work is lining up with theory. The intensity of the current is lining up. Now logically then, the R value should be equal to 5. So it's actually telling you from your graph that the slope is equal to the resistance of 5 ohms from this particular graph. So it's an ohmic conductor because the slope has stayed the same, the resistance has stayed the same. If you're going to try a different device, like for example a globe that we've got shown over here, you would find that the crosses do not do the same thing. So you might find that the crosses start to flatten out here and do something like that instead. Now in which case if you do that one there, you might be better off doing a curve of best fit through those points. And in that case the slope is changing all the time, so the resistance must be changing. You won't get the same sort of relationship. So just bear that in mind. You could also, so you could graph this the other way around. If you had the graph doing something like this instead, and you had the voltage is your independent variable, which is the normal way people do it, and the I is the independent variable, the dependent variable, you'll find that when you come to do this, if you did get a straight line, you can still do the same conclusion that voltage and current are proportional, but when you come to do your y equals mx plus c graph, this time you've got your I on the y-intercept. The slope here might be, for example, 0.2, and this will be 0.2 times by x quantity is v, and again there's no y-intercept. So this is a bit harder to work with because this is correct for your particular way you've done the experiment, which is a fairly typical way of doing it. Voltage is the independent variable, but to try and marry that to the Ohm's law one, which is v equals IR, requires you to rearrange that formula to make it look like the practical formula. So if you put it on the other side there and write it down as IR equals V, you need to still get this to look like the practical result, which is this one here. So I would leave the I alone, leave the V on the end then, just move to the end, and to get rid of that times by R it becomes 1 over R here. Now you should still be able to marry up the parts then. That current there matches with this. The y-axis values are matching, so therefore you should be able to conclude here that 1 over R this time is equal to 0.2. So those remaining values here, that part and that part, are actually marrying up together this time. Now to rearrange that you'll find that R will equal 1 over 2, or 0.2. So that gives you 5 ohms, which is the same way as you would have got before. Now you can compare that to the real resistor you placed in there to see if you get the same value and comment on the accuracy. So what we're saying is that you can get two types of conductors, the ohmic one and the non-ohmic one. The ohmic one, the resistance will always be the same, no matter what voltage is applied, and the non-ohmic one will change with the voltage. So some examples of that would be lights and computers. Most resistors, of course, are actually ohmic, whereas other ones like lights and computers are not. So what we've got over here is some examples of that. You can see these resistors here. The resistors have a typical colour code, and that colour code should give you the resistance, which should stay the same for different voltages put across it. And there's a couple of symbols for how it works there, to actually represent them. If you look at non-ohmic conductors like the light globe, if you look at the incandescent globe or something like an LED, you will find that they do not keep the same resistance for different loads, because the resistance changes. And the reason for that is, if you look at what's going on inside, say, the wire of the incandescent globe there, you'll got a picture, there's atoms going on there with electrons trying to flow through there to give you the current. If the atoms get hotter for some reason, by applying a higher voltage there, the atoms will vibrate more violently inside the actual wire, and it's more likely that the electrons will collide with those atoms in passing through the wire, so they get knocked backwards quite a bit and sideways, and that slows their current flow down the wire, and you get less current for the same sort of voltage, and that's why you'll find the resistance is changing. If you're actually getting a lower current for the same voltage, your resistance is going up, and that's why you'll find that slope curve going on in that previous one. The graph is going to go something like that, and you'll get less increasing current for the same increase in voltage, so it flattens out there. Now you can calculate all the voltages and currents in a series circuit by following some simple rules here. So what I've got here is 3 resistors in series, a 2 ohm, a 3 ohm and a 5 ohm. So we've got 1, 2, 3 resistors, and we've got a total there that we can actually find in the bottom there. So they're 2 ohms, 3 ohms and 5 ohms as resistance. Now in a simple series circuit, to actually work out the resistance, you just add those together. So it's 2 plus 3 plus 5, you've got 10 ohms of resistance there. In a series circuit, one of the basic rules is the current flowing around the circuit will stay the same all the way around because only one path. So you just got to use that as well. We know that we've got a voltage here, so let's say we've got, make it easy, make it 20 volts we're going to supply across here as a potential difference. So what I would normally do is I would work down the first column there and just add up all the resistances to get the total in a series circuit. I would then look across and do the totals at the bottom. So there's a 10 ohm resistor being supplied with 20 volts. So if you want to get the total current down the bottom here, you can rearrange Ohm's law. Intensity of current will be voltage divided by resistance. We've got 20 volts as a total across the whole circuit being placed through 10 ohms of resistance. So you've got 2 amps as your intensity of current. So having worked out your total resistance here, I will work on the bottom here and work out the other totals. It's 2 amps. And as I've just said, this is a series circuit, so using that knowledge here you can start to work up one of these columns. The thing that's constant in a series circuit is the intensity of the current. So you can place this here as a 2 amps and a 2 amps and a 2 amps so that you know exactly what's going on through each of the resistors. They're each getting 2 amps of current now. So we know the resistance in each one and the current in each one. So a simple matter to finish the table off and actually complete all the voltages for these would be to go across the column, the row. So you would then use the formula as a V equals IR to go across the row. And in that case here, for the first one, we've got 2 amps and a resistance of 2. You're going to get 4 volts being used in the first one. In the next one, if you look at that same idea, you've got 2 times 3, 6 volts being used in this next resistor here. And 5 times by 2 will be 10 volts being used across the last one. So 10 joules of energy per charge are being released in this last one. So you can see, if you check this out as a total, that all those totals should add up to 20. 4 plus 6 plus 10 should give you a total of 20 volts. So you end up using the 20 joules of per coulomb across each of the circuits shared. The one with the largest resistance, therefore, uses the largest amount of voltage or energy up. And you can see that then the 2 ohm one only uses 4 joules per coulomb of energy. But that's a good way of doing series circuits. Now you could take those 3 resistors and put them in a parallel circuit and again work out the total voltages and currents in each. So again we've got 3 resistors there, R1, R2 and R3, and they've got a value there of 2 ohms, 3 ohms and 5 ohms. So we can actually work out the total of those for the resistance and then the voltage and the current. Now this is a bit tricky because the total resistance in a parallel circuit is not just adding them up. There's a tricky formula here where you actually look at 1 over the total resistance. Will be done in fractions. You'll find it's 1 over 2 plus 1 over 3 plus 1 over 5. Now you can do that on a calculator just using the fractions button. So we need to find a common denominator to actually work out the total resistance here. So we'll try 30 there, because a half can be good to the 30 as 15, because 15 over 30 is a half. We can convert the 1/3 to 10 over 30, and we can convert the 1/5 to, if you do 5 times by 6 you get 30, so 1 times by 6 will be 6. So adding them together you get 31 over 30 for your total value there. So that means RT over 1, to get the total resistance, then you need to flip both of these over, and you get 30 over 31, which means you get about 0.9666 or 0.97 ohms as a total resistance value. So you've now got your total resistance in this column here. So you're doing the same sort of idea of working your way down the resistance column first. You now need to work your way across the totals at the bottom again like before. So if I give this a voltage of 20, same as before, so that total voltage down here is 20, we can work out the current again as I equals V over R. So you've got 20 volts over 0.97 ohms. So you'll end up with 20.67 amps roughly there. So if we put that in here as a total, and this is a lot bigger as a total now. And the reason for that you get a larger current down here is because you've got more pipes enabling the charge to flow down with more pipes. So the idea of water would be that you get more water flow down the pipes, you get more total current going down in terms of charge around an electrical circuit. So any one particular charge though would flow down only one pipe here and only go through one resistor, which means that all of its energy, all of its voltage there, the amount of energy per charge, would be supplied to only the one resistor. So you would expect that that first resistor would get all 20 volts going across through there, and anyone going down through resistor number 2 would do the same, and the same with 3. So the voltage here actually stays the same in a parallel circuit, whereas in a series circuit it's the current that stays the same because it's only going through one pipe. So this parallel circuit here you'll find constant voltage going across it, whereas the current splits up. So this current here will actually differ depending on the resistance down each of those paths. So how do you find the final sort of value here for the current? Using the same sort of formula here, which we'll use the blue one I think. So for the blue one here, to work out that last one you're going to go across the row here again, but this time you're working at a different sort of value. Instead of doing V equals IR for a series circuit, you're going to do I equals V over R for a parallel. And so you look at that, you've got 20 over 2 for the first one. So that means you've got 10 amps going down that first one. If you look at the last one, it's 20 divided by 5, you get 4 amps. And this middle one's a bit harder, you've got 20 divided by 3, which would be 6.6666, or 6.7. So if you look at those currents and add them together, because when they come back together here, you'll get the total again. And before they split up, you've got the total there. So that would be 10 plus 6.7 plus 4, you're getting around 20.7, which is what I've said here, 20.7 amps. So the current has actually split up, but it comes back together. So that should sort of match up. So you can use that table to work out parallel circuits and keep it organised. You can do the same thing with series. Just remember to go down the column to start with resistance, go across the bottom, and then you've got to make a decision of which of those ones do you want to go up. In the parallel circuit, it's the voltage that's the same all the way through, whereas in the series circuit in the previous page, you're going to go up the current one because that's going to stay the same.